Hello viewers, welcome you all. In today's lecture, I'm going to take the next topic of nuclear physics, and the topic is interaction of radiation with the matter. Right? So again, it is a very important topic in nuclear physics. Here in this topic, we are going to study how the nuclear radiations interact with matter. Nuclear radiations means the particle that are coming out of atomic nucleus. So if we look at the particle that are coming from the atomic nucleus, then they are alpha particle, beta particle, right, gamma rays, right, proton, neutron, right, deuteron, right, etc. So all these are the particles that come out of the atomic nucleus. So in this chapter, in this topic, we study in details of the interaction of these different particles or radiations with the matter. So first thing is, we can classify all these particle in two categories, right? One is charged particles, right? Charged means alpha, beta, right, proton or a deuteron, you can say, right? Uncharged, or we can say neutral. Neutral particles are very well neutrons or a gamma radiations, right? So these are two groups. So we divided the entire particles in a two category. Now I can further divide them into two categories. One is of three categories. One is heavy charge particles, and second is light particles, light charge particles, and the third category is neutral or electromagnetic radiations. Neutral or electromagnetic radiations. Now if we look at the heavy charge means those particles whose mass is very high or large as compared to the mass of electron. So the heavy charge particles are alpha particle, proton or deuteron. So this category contains these particles. Light particles, obviously electrons or positron, these are basically beta particles, fast moving electrons or positrons. Neutral, neutron or gamma radiations. So why we are doing this classification while studying the interaction of radiation with matter? It is very important because the interaction of these particles depend upon the behavior of the particle. First of all, we should know that what is the particle, what is its mass, what is its velocity, because the interaction depend upon the interaction time, and the interaction time depend upon the speed of the particle. Obviously heavy charge particle has low speed, so their interaction time is large. Light charge particle like beta rays, they have high speed comparable to the velocity of light, so their interaction is less. Similarly, gamma radiations or neutral particles, they are uncharged, so their interaction will be even smaller than the light particles. So this is the way, this is why we are dividing these particles or radiations in three groups, right? Now I will start one by one from the these three groups. So we will take the first case of heavy charge particles, right? So I am coming to the first category, that is interaction of a heavy charge particle with matter. So when we discuss the interaction of heavy charge particle with matter, you might have remembered, because I am not going into all the articles, the most important formula of this chapter is the Bethe-Bloch's formula or Bohr formula. That is for the interaction of heavy charge particle with the matter. We know very well, if have a heavy charge particle and it is going right in this way, it is heavy charge particle, suppose it is alpha particle, it is moving with velocity v, it has mass capital M, and when suppose it pass through a medium, right, it is passing through this going to pass through this medium, right? So when it pass through this medium, obviously it is going to interact with the electrons of the medium, right? So when it interact with the electrons of the medium, I mean it is going to exert a force on the electron, it is going to have a collision with the bound electrons, right? And obviously there will be a transfer of energy, so the heavy charge particle will lose its energy because of the inelastic collisions. So while passing through this matter or this medium, the energy of the heavy charge particle will go on reducing, but we are interested to find that what is the rate, right? Minus dE upon dx, energy lost per unit length of the medium. So this formula or this result was first calculated by Bohr, right? We call that as Bohr's formula, right? We also call it as the stopping power, S, stopping power of the medium. I told you why it is happening. When alpha particle is passing through the medium, alpha particle is a charged particle, it is undergoing collisions with the electrons because it is attracting the electrons toward its side. So obviously there is a inelastic collision, transfer of momentum and energy. So when the transfer of momentum of energy is there, the energy of the alpha particle is going to reduce. When the energy of the alpha particle will reduce, its velocity will reduce. Ultimately, the alpha particle can get stopped inside the medium, and then after it will take up 2 electrons and it will convert into a helium atom. So I am writing down the Bohr's formula that was derived by Bohr's, right? So Bohr formula is equal to minus dE upon dx. We also call it as the stopping power. This is equal to z square e power 4 into small n divided by 4 pi epsilon naught square m small m e b square log of natural log of e into 2 m b square upon h nu, right? In some books you can find in place of h nu, here it is written I. I will explain what is the meaning of I and bar. So this is Bohr formula, right? Now this formula was later on modified by Wath and Bloch by taking into consideration relativistic corrections, some quantum corrections. So then after we got the Bloch formula, Bethe Bloch formula, right? So Bethe-Bloch formula is basically the modified version of this formula, and it is equal to again stopping power, or you can say minus dE upon dx, energy lost per unit length by the heavy charge particle. It is equal to z square e power 4 divided by into small n 4 pi epsilon naught square m e, right, b square into log of natural log, that is e, this whole term bracket, into 2m b square upon I bar, right, minus log of 1 minus b square upon c square minus b square upon c square. So you can see in some books you can find in place of b square upon c square here beta square and beta square. So beta means b upon c, so you can write it in that way. So in this equation, this is slowly varying term, and this is the relativistic correction, right? So now I am coming to the different terms, different quantities involved in this equation. So as I told you, minus dE upon dx is equal to z. Z, what is z? Z is the atomic number of a heavy charge particle, right? Heavy charge particle. So in case of alpha particle, it is a 2, right? E is the charge on electron. N, what is small n? Number of electrons per unit volume of stopping medium, right? This is this. Now 4 pi epsilon naught square, you know very well. Me, mass of electron, right? Mass of electron of the stopping medium. B is the velocity of the heavy charge particle. So I think all the terms are clear. Here I was saying that what is I? I is basically, or sometimes we write it H nu. It is defined as the excitation or ionization energy of the electron of the medium. We can say excitation energy or ionization energy of the, in some cases electron can be even pulled out of the atoms, then it becomes the ionization energy. But in some cases electron can be excited to the high energy states. So this is the energy that we are representing as I bar, right? Excitation energy or ionization energy. You can write H nu or I. Right, B is the velocity, C is the velocity of the light. Now this formula is known as a Bethe-Bloch formula, right? So this formula is very important and it is valid for all heavy charge particles. Now I am coming to the questions that are asked. The question is asked that on what factors stopping power, or you can say minus dE upon dx depend. So you can see this formula that it is directly proportional to the square of the charge of the heavy charge particle. It is directly proportional to n, small n. N is what? Density of the electrons in the stopping medium. So you can say it depends upon the density of the material. Density of material. It is inversely proportional to velocity square. Velocity square means velocity of the heavy charge particle, right? So you can say, or if you take into the consideration energy, right, then you can say it is inversely proportional to the energy, because velocity is directly linked with the energy, right? So you can say it is inversely proportional to the energy. So these are the factors on which the stopping power of the medium depend, right? Or the, you can say, energy lost by the heavy charge particle depend. So usually question is asked from here. But you can see this formula. There is no dependent on the capital M. Capital M was the mass of heavy charge particle. So this formula is not dependent on the mass of a heavy charge particle, right? It is independent of it. Right? So usually, you can be asked that on whether it depend upon the mass or not, but it is clear that it does not depend upon the mass. Now, one thing that I want to tell you, in some books you can find here, in place of small n, you can see capital N or and Z multiplied. So capital N is what? Number of atoms per unit volume, right, in the stopping medium, and Z is the atomic number of that atom. So when you multiply this figure, it will give you the number of electrons per unit volume. So there is no way of bothering of it or getting confused with it. It can be NZ or it can be small n. So this is about the Bohr formula and Bethe-Bloch formula, and it is valid for all heavy charge particles, whether it is alpha particle, proton or a deuteron, right? Now I am coming to the Bragg curve, or that is again a very important Bragg curve, right? Bragg curve. Bragg curve is basically a curve or graph that is plotted between the energy lost per unit length, right? This curve is, you can see here, I'm drawing it. This is the distance traveled by the heavy charge particle in the medium, and this is the energy lost per unit distance, minus dE upon dx. Now if you look at the Bragg curve that we found, then it is found that this curve, you can see. Now you can look at this curve. From this curve, we can draw a conclusion that initially, when the particles start traveling through that medium, the energy loss per unit length was small. But as the particle travel further, the energy loss per unit length start increasing. Why it is increasing? Because it is dependent on a velocity. And as the particle loses its energy, its velocity decrease. So when the velocity decrease, the energy loss even more increase more, right? And that's why as we proceed further in the medium, the energy loss become more and more. Why? Because the velocity of the particle is decreasing, right? You can see here. So the particle will lose most of this energy at the end point of its journey, and then after ultimately it will get stopped. So we have to remember that while passing through a medium, the heavy charge particle lose most of its energy during the end time of its journey, right? So this was Bragg curve. Now I am coming to the range of heavy charge particle. Range of heavy charge particle. So we can calculate the range. Range means the average distance traveled by the particle before it comes to rest. So we can calculate the range from this by applying the proper boundary conditions, right? From this Matthew-Law's formula. So when it is calculated, it is found that range of the alpha particle, it has been calculated for alpha particle. It comes out to be, right, directly proportional to e power 3 by 2. Right. We know energy and velocity relation. Energy of the alpha particle, if we ignore potential energy, half mv square. So if I put it here, you can say R A directly proportional to B cube. Right. So we have to remember these two relations also. Range of heavy charge particle directly proportional to power 3 by 2, and it is directly proportional to the cube of velocity. Right. So this was the interaction of heavy charge particles. Now I am coming to the second part. You can see here interaction of a light charge particles, right? Now the second part is interaction of light charge particles. So what are light particles? Light particles are beta rays, right? And beta rays are nothing but fast moving electrons or positrons, right? So we know very well the interaction of the light charge particles will be different from the heavy charge particle. Why? Because their speed is very high. Their speed is of the order of 0.1 to 0.99 c. This is very important. And the other thing, now the interaction is taking place between the identical particles, electron, right? Positron, electron. When the beta particle passed through a medium. Earlier the interaction was different. So while passing through matter, these lightly charged particle can interact in three ways. The first is the same thing, inelastic collisions, just as the case of a heavy charge particle, right? And they lose their energy in the same way as this formula. We get similar kind of formula for the light charge particles and same kind of dependence, right? So what will happen here? The electron will interact with electrons, it will undergo inelastic collision, lose its energy, and minus dE upon dx will be directly proportional to z square. It is directly proportional to the density, it is inversely proportional to the velocity square, it is inversely proportional to the energy, right? But you can see from here that in case of electrons, as the charge is 1, z is 1, so here minus dE upon dx is small. In case of alpha particle it was 2, so it is 4, means alpha particle has 4 times more energy loss as compared to electron. Velocity of the electron is very high, so again the energy loss is small. So the energy loss of the electrons is different from the energy loss of a heavy charge particle, and these are the factors on which inelastic collisions energy loss of the light charge particle depend, right? But this first kind of process is dominant when the energy of the alpha particle is low. But when the energy becomes high, right, energy of a beta particle becomes high, in that case they can lose their energy in another kind of process that is known as Bremsstrahlung. Bremsstrahlung means braking radiation. Basically it is a German word, braking radiation. So when the energy of the electrons becomes very high, then there is a possibility that while passing through the matter, right, while passing through the matter, like this is the electron going, right, and when it pass through the matter, obviously it is passing close to the atoms, right? So there is a possibility that electron can penetrate deep inside the atom and it can come close to the atomic nucleus. So when it comes close to the nucleus, it is obviously attracted by the positive field of the nucleus and it get deviated from its path. So when it deviates its path, its energy change, and the decrease in the energy is radiated in the form of electromagnetic radiations. These radiations are in the X-ray or gamma ray region, and these radiations and this entire process is known as a Bremsstrahlung process, right? So this process is dominant when the energy of the electrons is high, right? The medium through which it is passing, it is also important that it is a medium of a high value of Z. It means the medium contains heavy nuclei, right? The field of the nucleus is very strong. I am writing here probability of Bremsstrahlung formula that it depends upon, it is directly proportional to small z square, capital Z square, E, energy of the electron, and mass square, mass of electron square. So here it will become mass. So small z is atomic number of electrons, so it is 1 for electron 1. So you can say it is directly proportional to Z square, E upon mass of electron square. Z is the, but Z I told you here, atomic number of the stopping medium. So large the value of Z, large is the probability of Bremsstrahlung. Large is the energy of the electron, large is the chances of Bremsstrahlung radiation, and mass is small for electron, so chances are more. So this is about the Bremsstrahlung radiation, right? Now I am coming to the third process, right? The electron can lose energy through another process that is known as Kernkov radiation. Kernkov radiation. So Kernkov radiation is basically the name given to the radiations that are emitted when a charged particle, fastly moving charged particle like beta particle, when it passes through a transparent dielectric medium, right, with velocity v greater than the phase velocity of the light in that medium. It is very important. The velocity of the fast moving charged particle is greater than the phase velocity of the light in that dielectric medium, right? So in that case, the radiations are emitted along the path of that particle. These radiations are known as Kernkov radiations because these has been first discovered by Alexeyevich Kernkov, right, in 1934. He was basically a Russian physicist, right? So now I am writing down the condition for Kernkov radiation. So beta particle, I mean electron, can undergo Kernkov radiation if the condition is E threshold value of the energy of the alpha beta particle is equal to mc square into square root of mu square upon 1 minus mu square. Here mu is the refractive index of the medium, right? So you can see here that the threshold energy of the beta particle for emitting Kernkov radiation, it depends upon these factors, right? If the energy is greater than this value, only then Kernkov radiation can emit, right? Another thing is that velocity of the particle, charged particle, it should be greater than c upon mu, right? Then we get Kernkov radiation. But if V is less than C upon mu, no Kernkov radiation will be emitted, right? So I told you in the beginning that Kernkov radiations are emitted only when the velocity of the charged particle is greater than the phase velocity or speed of the light in that medium, right? So these are the required conditions. One more thing about the Kernkov radiation is a Kernkov angle. We represent it as a theta c. It is the angle along which, right, if the charged particle is going in this direction through a medium, right, so it is the angle through which these radiations are emitted, right? So it is given as a c upon mu b. Mu is again refractive index, B is the velocity, C is the velocity of the light. So this is the expression for a Kernkove angle, right? So we have to remember all these things. Right. Now, this is the interaction of light charged particles with matter. Now, I am coming to the last one, that is interaction of electromagnetic radiations. Radiation with matter. So, as far as the interaction of electromagnetic radiation with matter is concerned, we know very well we can have three type of interactions. So, the first is photoelectric effect, second is Compton effect, and the third is pair production. Now you can see here the interaction of the electromagnetic radiation or gamma ray is different from the interaction of charged particle. Why? Because they are electromagnetic radiations. They are neutral. They are not going to interact like a charged particle. So their interaction is totally different, right? As far as these three processes are concerned, I think you have studied photoelectric effect in details in right from your 12th class. Compton effect you have studied in detail. I will discuss only pair production, right? But I want to tell you that what are the conditions for these three different processes to take place, right? I mean, what is the requirement? What is the energy requirement? What is the requirement for the medium? So, if energy is low, E low, and Z is high, right? Then we have photoelectric effect. I mean, the electromagnetic radiation passing through the medium will undergo photoelectric effect, right? And photoelectric effect, I want to tell you that it is a phenomenon of the interaction of the photons with the atom as a whole, right? Energy low means the energy should be less than 0.51 mega electron volt, rest mass energy of the electron, right? This is the one requirement. What is the requirement of Z? Z should be directly proportional to in this case sorry, Z not Z directly proportional to, but the probability of the emission of photoelectric effect is directly proportional to Z power 4 to 5. Means larger the value of Z, more are the chances of photoelectric effect. What the requirement is, the energy should be of this range, right? Now the second one is Compton effect. So for Compton effect, energy should be high, right? High. Z should be low, right? Now, what is high means? High means the energy range is from it is greater than zero point 0.5 mega electron volt, but it is less than 10 mega electron volt. So, if the energy is in this range, then we get Compton effect, right? And Z is low. Z is low means Compton effect probability P of a Compton effect directly proportional to Z. So, you can see dependence here on Z, here power 4 to 5, right? So you can see, so this Compton effect is dominant in those mediums where Z is small, but the energy of the electromagnetic radiation photon is of this range. And the one thing that I want to tell you, that the Compton effect is the phenomenon or process of interaction of the individual photon with individual electron. Here we are not taking into consideration the interaction between the atom and the photon. Here the interaction is between the photon and electron. We are considering electron as a separate entity, right? So this is the requirement. Now I am coming to the third one. Third one is a pair production. So for pair production, E is high and Z is also high. Both are high, right? So then we got a pair production. So high means E should be greater than, right, 1 mega electron volt. Actually it is 1.02. I will tell you 1.02 mega electron volt, and Z dependence is it is square, right? P pair production PP directly proportional to Z square, right? So you can see here that these different way of interacting of gamma electromagnetic radiation with matter dependent on the two factors, the energy of the photon and the nature of the medium. I mean, whether it is a dense medium or it is a lightly dense medium. Now I'm coming to the pair production. I told you, otherwise these two process we have studied in details. Now what is pair production? Pair production means when the energy of the photon, particularly gamma ray photon, we can say, it is passing through a medium, right, and it is gamma ray photon, it come close to atomic nucleus that is positively charged, right, you can see, and electrons are revolving around it, right, you can see here. So when this gamma ray photon come close to the atomic nucleus, I mean in the intense electric field of the nucleus, then there is a probability that this gamma ray photon can convert into an electron and a positron. This process is known as a pair production. It takes place in the vicinity of the intense electric field. So that's why I was saying that high value of Z, the nucleus should be heavy, so that there is strong electric field and there is an interaction between this electric field and gamma ray photon. So in that case, this photon will convert into energy will convert into matter, pair of electron and positron. But we know very well what is the rest mass energy of electron or positron. It is 0.51 mega electron volt. So if this process has to take place, then energy of gamma ray photon should be either equal to or greater than 2 times of this, 2 times 0.51 mega electron, because we are creating two particles. So it comes out to be greater than equal to 1.02 mega electron volts. That's why I told you here that it should be greater than 1.02. So this process is known as pair production. I want to tell you once again that it takes place only very close to the intense electric field, and the energy of the gamma ray photon should be greater than this energy, at least. Only then this process can take place. So these were the different interactions and process through which nuclear radiations can interact with matter, right? I classified them in three categories: heavy charged particle, light charged particle, and neutral particles, that is electromagnetic radiations. And these are the different ways of their interaction and some important points that I covered in this lecture, right? Usually questions are asked from these points which I discussed here. So thank you very much.